All right. Well, today our webinar is going to be focused on the assessment of final element assemblies. I'm Chris O'Brien. I'm a partner with exida, and I'll be leading today's webinar. My background is in process automation, high reliability power systems, and then functional safety consulting as well. What we're going to look at today is some things we've discovered working with our clients, both end users and OEMs, related to failure modes that we're seeing in final elements even after they go through a functional safety assessment and are designed and implemented in functional safety systems. So we're going to take a look at what some of the shortcomings are, what the causes are, and different activities that could be implemented to improve the reliability. As many of you probably know, exida is a firm that works with customers, and we work in three main areas. We provide tool sets such as Excellentia that help people implement the functional safety standards and do the design. We work with equipment manufacturers and suppliers to certify their equipment and process to ensure it meets the requirements of the standards. And we provide lifecycle services to clients and end users to implement those standards and implement systems. We're a global company. We have offices around the world, and we work in areas such as process plants, subsea applications, alarm management projects, autonomous driving in automobiles. So we've got a broad reach, and we work in a lot of different places that functional safety touches. Excellentia, as I mentioned, is our leading tool. It's an easy to use tool with best-in-class components that integrates the entire life cycle and leverages information throughout your organization. Excellentia is a full suite of tools that can do all the phases in the safety life cycle, and then also interface with different systems within your enterprise. In addition, we publish a lot of books and conduct a lot of training courses on a wide variety of subjects. So starting today, let's talk about, or let's look at what we want to go through. So first, I want to review the different problems we've observed with final element performance. Then we'll take a look at what are the root causes of that, how do we apply the standards to try to minimize or eliminate them, take a look at what we're calling a final element SRS, what that is and why is it required, look at verification and validation planning steps for final elements, then talk about what can be done to assess integrated final elements, and at the end, open it up for questions. So what problems are we seeing? As we're working with end users, we see the data come from both end users as we work with them in their plants, and OEMs as we do assessments and certifications. And the two, I don't want to limit the problems just to two categories, but the two most common things we see can be grouped into either the final element having insufficient torque or force to move the valve to the safe state when necessary, or failures of components within that assembly due to being stressed beyond the yield strength of the parts. We're showing here is a stem sheared, failed from excessive shearing forces. And the question, one thing that really comes up is, all right, if we're doing all this extra effort to design these functional safety systems or the safety instrumented functions, why are we seeing these weaknesses make their way into these assemblies in the field? If we take a step back and do a root cause analysis, now this is not an exhaustive one, but it's the beginning of one and kind of a summary of different things we've identified. So we can have a couple major areas. So the reliability or the functional safety, the safety reliability not being met. The valve can completely fail to move at all. The valve can not meet the performance criteria. It can move, but not meet the performance criteria. Or we could have a mechanical failure, as we showed in the photo. Any of these main branches are going to lead to a dangerous failure in the final element. So things that go about reliability not being met, I mean, the final element assembly can appear to be working properly, but it's not really providing the performance. So if you have invalid failure rates, you didn't design it to the safety manual, you're doing poor or no proof testing, or you're not maintaining it, that will undermine the reliability. Valve not moving. So these two on the left, they're a little harder to detect, because if you don't have a good program in place, you're not going to see them. But the valve could be too slow, or the valve may not meet the leakage criteria. So those are failures that may not be readily apparent. These other two, the valve not moving or the mechanical failure, you're going to see clearly. But the valve not moving, we've seen actuators being undersized, buildup of process material resulting in greater force being needed to move the valve, which results effectively in the valve being undersized, or loss of the availability of utilities in an application such as a dual acting actuator. And the mechanical failure, it could be a fatigue failure or a shearing from excessive force. And we've seen, these are actual things we've seen in safety systems installed in the field where they failed before they should have, obviously. Now, why? So with any of these, we can have the first reason, and then we can always apply the technique of the 5 whys. So, the actuator, or say the maximum allowable torque was exceeded. Why? Well, because too much force was put on the stem. Why? Because, and that could lead you down a branch that, oh, the actuator was oversized, or and in that case, you'd almost would say, if there's enough force to break the stem, it's probably oversized, or there was some defect in the stem, so it didn't have the strength. And you go through those 5 whys, and you go down to trying to get really what's driving this. Now, this is the HSC study on why control systems fail, and a very, if we look at specification and then design and implementation, and a little bit installation, but most of these failures, as we've looked at them, come back to specification and design of the system. So we're going to dig into that a little further, and we're going to look at different things that could be done to address it. The first question, though, is why aren't the standards catching these? And so the final element as a design subsystem kind of is a unique animal. If we look at, say, the 61511 SRS, it's going to probably not be detailed enough to do a thorough validation of all the things that could lead to these failure modes. If we look at 61508, the devices are going to have a detailed 61508 SRS, but they're going to address only the valve properties, or only the actuator properties, or only the solenoid properties, not the properties of the entire integrated system. So I've heard some people say, you know what, we need a different standard. 61511 doesn't do it, 61508 doesn't do it, so we've got this undefined area, we need a different standard. I don't think that's true. So let's take a look, for example, like at the 61511 SRS, we'll often get a top level requirement such as the valve will close, it'll have this leakage class, and here's the time it needs to move. But this really is, we could say, the final element assembly needs to achieve this. What I would propose is that final elements really are bespoke systems. They're going to be unique for each installation. They're going to need additional rigor than just the 511 SRS, and we can treat them as such, or if we treat them as such, we can define a process around them that's going to let us record our requirements and then test and validate we've met them. So if we look at what's coming out of 61508, we're going to get device level failure modes such as, something binds, or there's a loss of drive, or here's my pressure boundary for the valve. If we look at 61511, we're going to get the failure, we're going to get the requirements such as, well, the valve's got to close and it's got to have this leakage. But we need to get to kind of a functional failure for the subsystem. So we can see where with a 508 view, we might be we were focused on the device. At the 511, we're focused on the kind of the system performance, but we need a little bit of further clarification in between them. So if we look at what we call a tiered failure propagation, we can start over here on the right and we've got components. So we could have a ball and a ball valve and it's got these failure modes. If we build that obturator into a ball valve, the device has these failures. And so this is typically where 61508 is focused at. 61511 can be at a higher level like operational, a little more clarified than it's okay or failed, but more that, okay, the valve needs to close. And we need this functional view of what this final element needs to do in greater detail, and we need to specify that to move, I think, past this area where we're seeing failures in performance that we don't like. So we're proposing that a final element SRS should be created and should not only include the requirements, but should ensure that the steps necessary to design and integrate that final element are included. So if we look at that, so let's think about what they would be. We need final element requirements. We need to do an evaluation or that subsystem design. From there, we'll flow those things down to device requirements. Now, these things are well covered in a 61508. So if you've got a certified actuator or a valve, you should have the information at this device level. But not everything you put into a system is going to be certified, and that's kind of where this second bullet of the subsystem design comes in. We're going to have integration of the final element, factory acceptance testing, site acceptance testing, so inside integration and acceptance testing, and then ultimately operations and maintenance guidance. So looking at this little block, if we look at a bespoke system focused just on final elements, we can create a drawing like this. Now we're going to start with the SIF SRS. That is going to be that's our guiding document from for what we need to do. And so, for example, here's a SIF SRS, and from there we can pull out quite a bit of useful information or critical information for the final element. So, and just in this example, the valve will close on trip. The valve will have seat leakage requirements of class 4. Final element, the SIF needs to be 15 seconds, so we're going to take some part of that safety time and allocate it to the final element. We want to de-energize the trip system. We need it to be SIL 3. We want to run proof tests at 12 months or longer. And in addition to that, this is going to go into a boiler application, so we need to meet NFP 85. So NFP 85 is going to tell us double block and bleed for gas lines. And in our example, this is a gas line. Now that's a good start, but we're going to have to go further. And we want to think about this final element as really having its own V model. Now the V model, or that concept, the safety life cycle essentially drives a V model. where you need a specification, you need requirements, you need to do the design, you need to implement it, and as you're coming back up, you're going to have verification steps and validation. So for verification, we're going to check between each level that this required, and for validation at the end, we're going to confirm that the entire final element assembly is correct. Now, this is not a new concept, but it's something that I think is, to a large extent, overlooked in final elements. Part of that, I think, is due to the thinking that, well, we know how they work, we know what they do, therefore what we're doing is sufficient to get the reliability we need. That's a fine hypothesis, but the data and the results from the field are showing us that we're not really getting that across the board, because we're seeing quite a few failures. So let's look at, so we've got a requirement spec. Let's look at final element subsystem design. So the purpose of that is to understand what all the parts within that final element are doing and what their roles are. So two common techniques are CHAZOP or FMEDA. We want to clearly define the functions and requirements for each device or component within the final element subsystem. Now, really, I would say, we'd say FMEDA can, CHAZOP is a general term for control system hazard and operability study. You could say that, an FMEDA is a sub-technique of that, but we'll talk about them differently just for a section. Now, most times CHAZOPs are used probably at a control system level, not always at a final element level. They are beneficial if you've got a complex operating scheme where you've got control and safety interacting, say like in a batch process, and you want to really understand the flow of the information that goes to the final element and how it's being used and what could defeat it. A CHAZOP can be a very useful technique, and we've done it for exactly those purposes and those applications. Mostly we would do a failure modes effect analysis, where you start and you list the devices, the components or devices, what are their functions. Now, this FMEDA is structured really to understand and drive functional failure modes and identify potential diagnostics. So, lots of ways to do an FMEDA, all use a similar methodology. But here, so let's say, just in this example, we've got a test solenoid, a bladder accumulator, a trip solenoid, and a needle valve. So this is only one part of the system, but it's kind of the trip part of the system. And you want to be able to implement a partial valve stroke test by bypassing some of it. So you would list each device in your entire final element, you would describe what their function is, and then think about, well, what can fail within that element? So in a solenoid, so we could have a coil open, we could have binding, we could have loss of reset force, we could have external leaks. For those functional failure modes, what effect would it have? How would you classify that? Is it a safe failure, a dangerous failure, a no effect failure, an enunciation failure? And is there a potential diagnostic or test that you would use to detect it? So this is really an important step. Now, if you've got a standard, hey, I've got a solenoid and I've got an actuator and a valve and the coupling in between, that's pretty straightforward. There's lots of systems that are dual acting. There's lots of systems that have other logic in them. And when you get to those, doing that FMEDA, or if it's maybe a batching system with other things, a CHAZOP is a key step to defining the requirements or the functions. Once you have identified all the devices and whether they're safety critical and what they need to do, we need to have device requirements. And I think this is probably the biggest gap between what people do today with the SIF SRS and what we really need to do to drive greater reliability. So we really should have a cascading requirement step. So we could take from the SRS, we have, closed block valve and open vent valve. So we said it was NFP 85, so we know we have 2 block valves and 1 vent valve. Well, for the block valve, we're going to have leakage requirements. Then we're going to have things such as torque requirements. And we'll touch on this a little bit today, but we'll have another webinar just on this subject. But with torque, we've got breakaway torque, maximum torque. Those are 2 things that are pretty well understood today. However, we do see, we've seen cases where brand new valves have been installed, and within the first month they've sheared the stem off. And these are safety rated valves and safety applications. So even just properly sizing that actuator to the valve doesn't happen all the time. I think what happens is a lot of times people will over design the actuator because they're concerned about increases in torque over the mission of that valve, but they can be, you put too large of an actuator on it, you're going to and the stops aren't set, you're going to shear that valve stem. So not only is there breakaway and maximum torque, but then also mission torque requirements. And so that's, how does the torque change over the entire time that valve is installed? How do those requirements change? What's the maximum stem strength? Now, these are not exhaustive. These are, what I've tried to do here is capture the things that aren't maybe reviewed as in much detail as they should be. Then we'll have, for that block valve assembly, we'll have a spring return actuator. We need to understand the minimum torque output and the maximum torque output and be sure that it'll meet the requirements. We have a de-energized certificate solenoid. What's the CV through there? Will it exhaust fast enough for the assembly to move quickly enough? Then we get into stuff that often isn't, I think that is often just designed, the way it's always been done. Mounting brackets and coupling. So what are the dimensions and the strength and the deflection of those additional parts that go into the assembly? Now, if there are other parts like quick exhaust valves or other things that are needed for that final assembly to work, we would cascade those requirements down to these specifications. Each of these specifications now would have, there would be a maximum stem torque strength of 10,000 pound torque. Then you could validate that or verify that with the valve design or the valve OEM that it's met. So if we get more precise requirements, we could do a better job of verifying them. This is just a little preview, but like a mission torque requirement, it's going to be the sum of the design dependent torque, which is essentially what's the friction and the bearing parts within the valve. What is the dynamic pressure and flow induced torque requirements. Now, these first 2 are reasonably well understood and often well documented in the valve literature, valve and actuator literature. So here we've just got a graph. AWWA has a very good standard, I think it's M-49, where it looks at cast iron valves in water applications because it's Water and Wastewater Association, but it gives a methodology for calculating requirements, especially as you get into bigger valves where they're harder to test. But there's design. If we look at here, here's dynamic torque based on flow going through the valve. This is an example for a 24-inch butterfly. Here is design torque, the friction torque within the valve, and that friction torque will vary depending on the orientation of the valve. Then whether we're opening or closing, so here's the maximum opening torque required because we're going to have to overcome the flow. That's, in this case, the flow is tending to close the valve. So this is the opening torque requirement, and this is the closing torque requirement. So right here it's negative, which means it's kind of acting to close itself. There's enough dynamic induced torque to close it. So that's only touching these first 2 things. Then there's three other things to consider. So one is the application. So is there a physical or chemical reaction or change going on in that valve as it's in process or service for a long time? Then there's time dependent. Valves that are moved more frequently will have a lower stiction or binding forces. Now that in our FMEDAs and in the exida FMEDAs, we have that available, as you can get a dynamic as well as a static analysis. And then also there can be integration torque or misassembly or misalignment or mismaintenance torques that result from less than perfect design and integration. So the overall torque requirement for that valve for being in service 15 or 20 or 25 years is the sum of all of these 5 contributors. So I think that we know that inherently, and that's often why there's a tendency to maybe, if we don't account for it, we can get the situation where the valve doesn't move. If we over account for it, we can get the situation where we're putting an actuator on the valve that's too large, and that's causing its own set of problems. But we'll have a separate webinar just on the torque on this topic in a few weeks. But for today, just suffice it to know that that's out there. Now, once we've defined that, we're going to have other parts such as couplings and assemblies, and they need the same rigor applied as the main parts of a solenoid or a valve or an actuator. So are we looking at the bracket and coupling strength? Are we looking at deflections? Are we looking at yield strengths? Are we looking at what kind of diagnostics we get or we can claim in the different proof testing? Also in the design phase, we're going to have SIL verification, and then in that case, any component that's part of the assembly has to be included. We got to confirm, and from our FMEA, we're going to know what parts are safety critical and what the failure modes are and if they're safe or dangerous, so we can model it correctly during our SIL verification. We need to use good failure rates in our SIL verification, of course. Multiple different sources. We think the Safety Equipment Reliability Handbook, which is embedded in Excellentia, or FMEDAs are the best place to get detailed information. If you don't have that, there is silsafedata.com, which provides kind of a minimum and maximum, and you can at least do a reality check to make sure you're using a reasonable number to model the different parts in the assembly. Devices need to be certified or based on proven in use if they're in a SIL rated application. So again, looking at the safety automation equipment list is going to give you that information. Then as we're still in the design phase, we're going to be modeling, or in the SIL verification, we're going to assume and model proof tests, and depending on what proof test we're using and what diagnostic we might be using, we're going to have different coverages. So here are 5 standard proof tests for valve assemblies that we've defined at exida, not defined, that we typically model at exida. So you could have a partial valve stroke, you could have a full valve stroke, you could have a full valve stroke at operating conditions. That's going to get more of the dynamic forces will be being applied, so that's going to be a more thorough test than if the flow isn't happening. And then for the 4th and 5th, we can take the full valve stroke and add a leak test, and then finally do a full valve stroke test at operating conditions and add a leak test. So depending on the proof test, we get different coverage. So here we have the 5 proof tests. And here we have functional failure modes. Again, these are the, how does the component failure within a valve express itself? How would we detect it from an application perspective? And then depending on the proof test, we're going to have different coverages. So we want to make sure we put we use the proof test that's going to be used in the field, and that we use the right coverage. And so, for example, if we take just a ball valve with a nominally 575 fits failure rate, depending on this proof test, we can have a dangerous detected from as low as 201 fits up to essentially 99% coverage. So depending what set of numbers you use, you're going to get a very different SIL PFD average calculation. So that's also important. This is just an example. Can't use it on, this was a close-on trip application. Wouldn't be applicable. These numbers aren't applicable to tight shutoff or applicable to fail open, because each of those have a different distribution of those failure modes. Now, we've specified it. Now we're going to integrate it and do factory acceptance testing or site acceptance testing. And it's required in all cases. What might need to be done could be pretty different. So if it's a, on the left-hand side, a very unique bespoke system kind of built in a, maybe not a controlled environment, you're going to have a different set of requirements than if it's, say, a standard integrated assembly from an OEM. And some of these assemblies are already certified, so a lot of this sizing would be done. So there are some valve actuator combinations that are certified, but what we really get to is, at this point, is what's the correct verification and validation planning. And so integration testing and review, factory acceptance testing, site integration, site acceptance testing, all of the same things need to be reviewed, or all the requirements that we've talked about need to be reviewed. But depending on what's done where, the plan's going to look a little different. So I think the most useful thing to do is to say, what does a verification and validation planning, robust plan look like, and then where do we do it? So we've taken each of these steps we've talked about. So the final element safety requirement spec, final element subsystem design, device requirements, integration, factory acceptance testing, site integration, site acceptance testing, and operation and maintenance, and done, for example, what's the requirement we're trying to validate? So we'll start simple and we'll say, well, let's take a final element SRS. Well, what are we trying to validate there or verify there? We want to make sure that the SRS is correct. Typical techniques you're going to use for that are, or things you can do to minimize errors, is you can, hey, we're going to use a template. We're going to inspect and approve that template and put it under version control. And every time we fill that out or create a new SRS, we're going to have an independent peer review or 1/1 review to confirm that we've captured the right information in that template. We look at final element subsystem design, design analysis. We're going to do a functional FMEA. Which is going to give us our devices and components, and then what functions are they performing and how could they fail. So fit for use, we're going to look at the specifications, the IOM, and the safety manual review to make sure that it appears to be the correct design. SIL capability, we're going to look for a certificate and an assessment report. Architectural constraints, we're going to look at the FMEDA report and see what it says we can do. And PFD average, we're going to use a tool like Excellentia or use a good technique, and we're going to look at the failure rates to be sure they're reasonable, and then do that SIL verification calculation. For device requirements, we're going to create that detailed or cascading requirement, and really the way you would number them is you would go, block valve was 3 levels in, so that's 1.1.1, and then we've got the leakage and breakaway torque and all of those. So for every requirement we've got at the device, we've got to have the justification that that's met. So if you're buying a certified valve, most of the, or a certified device, most of that information is going to come with it. So for example, leakage class, that's going to be a design qualification, and most valve manufacturers are going to do an end of line test for leakage, and you'll be able to get, you know, their technical manual, their safety manual, their certificate, and request an end of line test data sheet. Where it gets grayer or more difficult, and I think part of the reason we're seeing problems in the industry is, you know, breakaway torque, maximum torque, there often will come out of a design qualification, but maybe we need an end of line torque test for a valve we're putting into a safety system. So the design may be validated, but there's going to be some variation, and we might ask for production measurements of that. Mission torque requirement, that is not going to probably be, that cannot come completely from the OEM. That's going to have to come from understanding your, as an end user, what you've got in the field. Is your process reacting with the materials? Do you see things change over time? So field failure studies, proof test results, you know, as we get better, not better, but more specific generic reliability studies, we can probably start giving some guidance on that, but that's an area that needs some focus. So likewise, in the device, any requirement is going to have to be validated. In integration, the assembly will need work instructions and routings, and the testing, they'll need test procedures and results, factory acceptance testing. So that functional test, depending on the complexity of the final element, you know, might include hydraulic power units, et cetera, or it might be simply just an integrated valve actuator. Documentation review, we might look at material certifications and the results of all these previous tests to show that they're covered. Site integration and acceptance. Now, if all the steps prior to this have been done, we're not trying to validate so much the design of the final element, we're just trying to make sure that that assembly is properly installed and working. So in one case, that might just be more the classic installation validation, but if these other steps aren't done, that's going to have to happen as well. And then in operations and maintenance, it's going to be, there's got to be proof test procedures, they've got to be executed, they've got to be recorded, and we need to be maintaining this valve assembly to the manufacturer's recommendations. So, you know, this kind of breaks down things that are done maybe semi-formally or informally, but in most cases are not done in a formal means. And I think if we go back to our root cause analysis is what is driving these failures, you know, better you know, a more thorough specification and a robust verification and validation plan to make sure those specifications are met is critical. So how do we find this, or how would we assess this? For OEMs, typically that's an extension of a 61508 certification. They'll often have one for their devices, and then adding that integration process in there, ensuring that they're doing the right steps would be the way to do it. For a valve integrator, it'd be a 61508 certification as well. As an end user, they're not going to be certified, but it's going to be an assessment. It'll be a 61511 assessment. In all cases, the stuff we've just looked at, we would look, exida would look for, you know, the exact same thing, whether it was under 508 or 511. So if we think again back to that slide about this area between the two standards, what we're really talking about is final elements as a bespoke system, which can be addressed by 61508 or addressed by 61511. The most critical thing, though, is the proper specification, execution, and then verification and validation planning. And we really feel that that's, you know, as we've looked at this, this is stuff that could be added that's going to result in a more reliable final elements. So at this point, we can move to questions, and let me get the question I gotta, here we go. Okay, questions. All right, so here's a question. Are we finding that companies are asking for certified assembly? Yes, in fact, and we've seen an increase in the in the number of requests, and we get it often two ways. We'll get it either there's a specific project and they would like a third party to go and kind of do a validation or FAT witnessing and assessment, and or we get a general requirement to get a process assessment done. So here's another one. In the context of the SIS lifecycle, who will be responsible? Who's the responsible party for planning, executing SIS validation activities? Designer, manufacturer, or supplier? Now, in the standard, the answer is that responsibility can be assigned. So any step in the life cycle could be done by any competent person or organization. So there needs to be essentially the functional safety management plan needs to say who owns what activity and ensure that they're competent and that they do it. So the biggest thing that I'm seeing is not so much that it's almost like an understanding that you just can't say, give me a valve, and in most cases it works out okay, but it isn't necessarily rigorous enough for a safety system. And I think that's why we're seeing these failures in safety systems. So it could be the designer, manufacturer, or system supplier. Probably. So I would just be a little clearer on what validation activity. So if it's validating the final element, it's either going to be, it could be anybody, but whoever integrates it probably could do a big chunk of that validation. But that isn't stipulated by the standard. How do you rate the quality of failure data for final element assemblies? Often the system suppliers or even certificate seems ambitious. Well, that's a good point. So I would say I'd say this, and not just because I'm part of exida, but I think exida has done really an amazing job of validating data. We've collected over 250 billion hours of field data, and we take that and we calculate the the apparent failures, remove things that might be systemic versus random, and basically calibrate our FMEDA technique. And every time we do a certification or every time we do a renewal, we'll take that FMEDA number we've generated and do another study of, we do 3-year renewal audits of the last 3 years of performance, and they've really become pretty well calibrated. Now, there are other certification agencies that are using different techniques and are, frankly, too good to be true. So I think it depends. It all depends on where you're getting the data or who's supplying it. So you do have to be careful. How often do proven in use or self-certified devices exceed their failure rate? Well, I think that I don't know that as a number. I know that it seems to be getting a little better because people are people are getting sensitized to the ambitious failure rates. But I'd say probably 75%, if not higher, of all self-certs that I see or have ambitious numbers on them. Because what many people will do is they'll do their, an OEM will make an assumption, well, I shipped 10,000 valves, I only got 15 back, and I've had, on average 10,000 valves in service for 10 years, so that's how many hours of operation I have, and I only have 15 failures, so if I do that math, here's what I get. And what they're assuming is that every failure is detected, every failure is reported, and everything runs for as long as it's been since it's shipped, and those are optimistic assumptions that result in optimistic failure rates. I've been forced to put building utility filters with monthly change out to protect instrument error. Does this PFD have to be figured into the system reliability? So, yes, but what you're probably doing is dramatically improving the system reliability. So if, and the question would be is if that error is a utility that, say it's a dual acting actuator and it needs that air, then the availability of air absolutely has to go into the reliability calculation. And then your but that maintenance program sounds like what it's doing is it's very much improving the reliability of air, and you would have some factor of, even with maintenance, you wouldn't assume it's perfect. You might assume it didn't quite get done, and so you could factor that in. And in Excellentia, that's what we term site safety index. And it takes into account the possibility of critical maintenance not being done. If the final element is identical to the one which I'm replacing, do I need to do a SIL verification? Short answer is no. Full answer is anytime you touch a safety system, you should do a management of change and essentially an impact analysis, and you go, state A is this, I want to go to state B. The difference between state A and state B is XYZ. And in this case, you go identical equipment, first valve was certified, valve still certified, I can use my existing analysis. Most ops groups oppose leak tests. What percentage is exida seeing for leak test? I understand that concern. I remember back 20 years ago, 25 years ago, it's like, don't ever talk to me about, partial valve stroke test. Oh, leak test, not valve stroke test. Really, I see that done when that's going to save hardware. If that's going to save putting redundant valves in, and you go, this is what we need to do to meet our safety requirements, then people do it. If you don't need it, then, and typically that's often more on a tight shutoff that might be needed, then, and often tight shutoff by NFPA is supposed to be having a yearly leak test anyway. So I see it there. I see different things too, like bottle checking. So different equipment, sometimes you can lock in a pressure with a transducer and read that depending on what failure rate you're trying to find. So I don't really know a percentage. I know it usually, it's not where people want to start. And then it comes down to if doing that a more thorough test is going to avoid having to install a second valve, then that's considered. My issues have arisen from utility issues, rust seizing the solenoid. How far back in the FMEDA do we customarily go? Yeah, I don't quite understand that. I said surges of rust seizing the solenoid. So the FMEA would be, what's the function? So that would clearly articulate that. And then I think if the solenoids are rusting, so I'm not sure by surges if you mean it's periodically, every now and again you get it, or holistically you have it. So I don't quite understand that question, and so maybe I can follow up separately on that. Um, so the test first that we showed of having 60%, whether it's a proof test effectiveness or diagnostic coverage. So that's an interesting question. So is that effectiveness we showed for the those tests, are they proof tests or diagnostic coverage? And the answer is they could be either. So if it's implemented as a proof test, then we would model it that way. If it's implemented as an automatic diagnostic, so it runs automatically, it can be detected and enunciated by itself, it could be treated as a diagnostic, and then you would recategorize it from dangerous detected to dangerous undetected. The impact on PFD average is going to be the same. If you ran a diagnostic, every 6 months, or you ran a proof test every 6 months and they were identical, your impact on PFD average, I'm saying it's going to be identical. There might be some minor thing like, when you're in a proof test, you're not running, so that time it's in the test, it doesn't count towards it, but you're not going to see any difference in PFD average in any significant digit. The challenge is to meet the timeline in a tight EPCC project. Do we foresee the engineering phase will be prolonged much longer when more emphasis is put on the final element SRS? It will take some additional time, but I think if we get this into how things are done, and so, final elements are somewhat repeatable. They're not identical, but they're somewhat repeatable. And so not everything will have to be a from scratch analysis or done. And it's true it's going to take more planning time, but we have been involved in multiple projects where we've been brought in after, where the plant's going to commissioning, and people are then trying to say, oh, well, we need the right paperwork and we need to make sure the proof tests are right, and the equipment that's selected isn't correct. Or, the case of the valve stem shearing off, that was at commissioning. So it does, and it's true that not every project witnesses those experiences those problems. So, but we're seeing enough of them, and we're seeing a relative push in the industry, multiple places, to say, this is a pretty broad, this is just pretty broad spread. So I think that, if valve integrators and OEMs get the process in place, it really can become just their normal way of doing it. You clean up the weaknesses or the misses once, and you can apply them across many projects. Certificates over the valve assemblies are based on prior use data from plants. No, I would say that the exida methodologies, we would do an FMEDA. Now, the FMEDA is a component level, is a modeling, a predictive technique for those devices based on a component database that's been validated with 250 billion hours of analysis or field data. So we've broken down that field data and mapped it to things like O-rings and springs and castings. And so if we have a new design, we say, all right, here's our published failure rate for a two-piece floating ball valve or a three-piece ball valve body. And here's the failure rate for a spring. And we build it up that way. So it's a highly validated data source, but it allows us to do predictive modeling on designs. So what artifacts are expected for operating plants in this area? I would say the biggest thing that's going to have to, that's needed, is that traceability of proof testing or field operations against different chemical and operation profiles. So it is required to do the testing and record it, and to demonstrate that the safety functions are performing as well as the design said they would. And I think that the artifact would be those test results, But then the benefit as we aggregate those test results will be to say, oh, we can see that, you know, stainless steel valves in this application failed 25% more than in a benign application, and we can start getting some application factor data to apply. But I think the artifact required would be, you know, installation and validation, site integration and site acceptance testing, and then the periodic maintenance and testing that's required. Yeah, this is a great group of questions. Thank you. So let's see if I've missed anything. Let's just see. There's a couple more. Let me. So do you feel? I feel a lot of effort is put into SIS design verification, but raising the question on proper maintenance procedures and reporting, the door becomes closed most of the time. Well, it's true. I think that's the next big area is, you know, some organizations are very, you know, they've got it in their DNA and they're doing it. And we've talked to people and they say, you know, we're never going to do it. We're not going to do it. It's like, okay, well, you're not going to, you know, you're not going to meet the requirements. So that is true. I think that's the next area. And then another question. Has exida certified assemblies of integrated final elements together before? Yes. Actuator, pneumatic, circuit, and valve. Yes, we have. A lot of that has been specialty valve assemblies, especially, you know, trip assemblies for turbines. But there's quite a few. So for the whole thing, like with a, you know, a trip manifold assembly, a valve, an actuator, we've done that. And then more common would be an actuator integrated to a valve. And there's a category in Excellentia for integrated valve actuator assembly, and that's a place you could see some certified ones. So some of those have been integrated, have been certified as standard devices available, and then some have been certified on specific projects. Yes, and I think we're going to see, I think we as the industry are going to see more of that, because there is, I think as people see these failures, there's more of a push recognizing this is an area that needs to be tightened up or would benefit from a little more scrutiny. Well, great. Well, we'll make the webinar available, the slides and the recording. And any questions I didn't get, sorry I don't have my email on there. I'll put that on. But it's cobrian@exida.com. Feel free to reach out to me. And appreciate everybody spending a little bit of your time with us. Have a great day.